Welcome back, everybody. Today we are going to get serious. We're going to get into the details of the register file card design and the logic and the choices that were made there. And this is the testbed simulation model for the register file card. As you see, there's a lot more here than the previous time. We are going to walk through this together. It is ultimately simple. And let me say this as a sort of an introduction to this episode. If at any point you feel intimidated by seeming complexity, remember the previous episode. Remember that ultimately this is a very, very simple circuit, and that the seeming complexity is just because of some housekeeping details. It's nothing too big. If you spend some time on your own with the schematics or with these simulation models, you will see how simple it is. It may seem complex just because I'm just showing you everything at once, the final result at once. So it may seem complex, but it isn't really. So let's start from the basics. These are the registers that we've seen the previous time. Let me switch this to this mode. These are the four registers: AL, AH, BH, AL, and BL. Each of these registers can receive a value from or drive a value into the internal buses. And this is the internal bus high, the high byte of the internal bus going vertically here, off to the left of center. And this is the internal bus low, the low byte of the internal bus running vertically off to the right of the center. Now, values from this bus go into the two registers connected to it. So the high byte of the bus goes into BH or AH potentially. And the same for the low value on the bus can go into AL and BL. And in turn, each register can write back to its own bus. So if AH has a certain content that we want to see in the bus to be shared with other system components, the values of that register go through this buffer down here, and becomes available on the high byte of the internal bus. Same for BH. It comes down here through this buffer, and it's then available to everybody else on the high byte of the bus. Same about the low registers. AL, the content of AL can go here through this bus and be written into the low byte of the bus. And BL, through this buffer here, the value can be written into the low byte of the bus. And as we've seen before, contents of the internal bus, either the high byte or the low byte, can be written into the external data bus, which is represented here at the bottom. This is the external data bus. Now, what have we added here compared to last time? Some very simple stuff. For instance, we now add this buffer. There is one for each register. This is for AH. This one here is for BH. This one here for AL. And this one here for BL. Each of these buffers drives an LED bar. And you see the four LED bars here, here, and here, driven by its own dedicated buffer, so we don't have overcurrent coming out of any IC pin. This is just to visualize the contents of each register on the respective LED bar. That's all there is to it. There is no computational functionality here, it's just to visualize. And the contents of each register also go to the ALU directly, bypassing the internal bus. So I added a little buffer here because this register may not have enough oomph, enough drive to drive the signal through the two backplane connectors all the way to the ALU card. So to make sure that we don't have signal level deterioration or excessive signal level deterioration, I added a little buffer. This buffer is continuously enabled, and the direction is also grounded, which means it goes from B to A, so the direction is like this, from top to down, towards the ALU. The LED drivers are also continuously enabled. Output enable is grounded and direction is grounded, so it's always from B to A, so it's always to drive the LEDs. So this accounts for, what I just said accounts for these 8 buffers here. They are just to drive the LEDs and to drive the register values to the ALU board bypassing the internal bus. Very simple stuff. What else have we added? We added some stuff here at the top. Ignore the noodle logic for now. Let's look at the stuff here at the top. These two buffers here are also constantly enabled, and the direction is grounded, so it's always from B to A. And all they do is drive two more LED bars, here and here. That's all there is to it. So we can visualize the contents of the bus next to the contents of the registers. So these two only to drive LED bars, no other functionality. And then I added two deep switches, here and here. And of course we need a buffer to drive the contents of the dip switch into the buses. So we have the dip switch for the high bus, goes through this buffer, and here the dip switch for the low bus goes through this buffer into the low bus. And that's to enable us to use this board in standalone mode and just play around with it to see how it works. And then finally, these two extra buffers at the very top, their function is to connect to the rest of the internal bus off the register file card. These two lines, vertical lines here in the center, they are the local segment of the internal CPU bus in this register file card. But other cards also have the internal bus of the CPU. So to connect this local internal bus, I'll call it the local bus from now on, which is the local segment of the internal bus. To connect the local bus to the internal bus of the other cards through the backplane connector, we have these two extra buffers here on top. And they can either drive the contents of the local bus out to other cards, or they can drive the contents of the internal bus as defined in other cards into the local bus here. So the direction bit is no longer grounded. The direction bit now of these two buffers here is programmable. So we can determine whether the local bus is transmitting or receiving information from the external, from the internal bus of other cards. Quite simple. Now, this stuff here off to the side, that's the control logic. And all it does is to make sure that there are no bus conflicts. This is just for bus arbitration. That's all there is to it. And the best way to explain it is to just test this, simulate this, and show you how it works. It's the best way to do that. So let's increase the size a little bit so you can see the values. These are the control values. B high load enable, A high load enable, internal bus high output or IO enable, B high output enable, A high output enable, and the same thing for the other side. And this is the external data bus input enable. So these are the control bits that will ultimately come from the decoded instruction word, which are used to control the whole the entire circuit here. All right, so how does this work? Let me switch to the little hand so I can play around with it. The first control bit, which will be just a shunt pin header on the board, is to determine whether we are using this board in standalone mode or in system, connected to the rest of Talos. If it's 1, this is positive logic here. I'm using positive logic here. If this is 1, it means the board is in standalone mode. If it is 0, the board is in system. Now notice the following. These two buffers here, which connect to the two dip switches, dip switch high, dip switch low, and these are the two buffers that drive their values to the internal bus or the local bus. These buffers should be enabled only if we are in standalone mode. Because if we are not using the dip switches, and these two buffers should be completely disabled. Now the direction is fixed. You see the direction bit here is grounded here and grounded here, and that's why we always drive from the dip switch to the bus, not the other way around. The dip switch is not an LED bar. And here it's the same thing. It's always from B to A when the direction bit is grounded. So in this case, the chip is upside down because this is the LED bar. So you always drive to the LED bar, not from it. And in the case of the dip switch, you always drive from the dip switch, not to it. That's the only rationale. But we need to enable or disable these buffers depending on whether we are in system or not, or standalone or not. So if I come here, standalone is 0, so we are not in standalone mode, we are in system. And then light green on this line means that it has a logic 1. Same thing here, light green is a logic 1. And this is the output enable outputs of the output enable input of the buffers. And since they are active low, 1 means that these two buffers are disabled, they are tri-stated when we are not in standalone mode. But if I go to standalone mode, these lines here change to dark green. Dark green means a logic 0, dark green here as well. These buffers are now enabled and we can use the dip switches. And this whole thing only depends on whether we are standalone or not. Now, let's put it in system, so not standalone, and see the rest. Now, when we are not in standalone mode, these two buffers here are enabled. You see the direction, the output enable line is dark green. Dark green means we are at 0 and it's active low, output enable is active low, so we are enabled. So these buffers will be turned on, they will not be tri-stated when we are not in standalone mode. Therefore, they will connect the local bus here to the rest of the internal bus across the other cards. But the direction is important. Right now, all the other control bits are disabled. Let's look at the direction. The direction is dark green, so that means it's ground. That means it's from B to A. So it takes the internal bus high off this card and connects it into the local bus high. And on the other side, the same thing. It takes the internal bus low, the signals that come from the backplane connector, and drives them into the local bus low, because the output enable is active. What happens, however, if one of these registers here, one of the 4 registers, wants to drive the internal local bus, wants to put a value on the bus? If this would still be trying to drive the bus from the outside in, we would have a conflict. So if we enable any one of these buffers here, this, or this, then the direction bit should change, because now these buffers should take the value of the local bus and drive them out through the backplane connector to communicate it to the other cards via the internal bus. Is that what happens? This is what's done by this little logic here, three TTL chips. So let's check. Let's say A high output enable is now go to 1, will be active. Then this direction bit here and here should go to light green, such that it drives from A to B as opposed to B to A. Let's see. You see, it's light green now on the high byte, because A high is writing now via, let me see, via this buffer here. Output enable is now active via this line here. It's driving only the high byte of the local bus. Therefore, this buffer here has its direction changed. Not the other one, because nobody is writing on the low byte of the local bus. Now, if I bring this back, the direction changed again, so now it's an input as opposed to an output. But if B high tries to drive the high bus, see, the direction changes again. So now the value that B high puts on the high byte of the bus will be driven out from A to B to the other cards. So the other cards know what value B high is putting on the high byte of the bus. Now, if I activate both, this is not allowed, because you cannot have 2 bus drivers, but you still have the correct direction. Now, there is one other case in which we have to change the direction of this bus, and that case is when we are reading from the external data bus and putting a value on the high bus. And the same for the low bus, when we are trying to put a value on the low bus coming from the external data bus. How do we do that? Well, first we have to enable the output of the respective bus. Let's say we want to put the value of the external data bus into the high byte of the internal bus. Then we have to enable this buffer. Output enable has to go low, because it's active low. And the direction bit has to change to 1, such that it goes from A to B as opposed to B to A. So these two signals have to be changed around. And once that happens, then we'll be driving a value into the high byte of the bus, and now this has to become an output driver. So the direction here has to change. Let's see if it will change. If we just say internal bus high IO enable, now we know it's an IO, but it may be an output, so we don't need to change the direction. But the moment we go to external data bus input enable, now the external data bus should be driving the high byte of the local bus. And the direction bit would change, because now that value has to be taken from the local bus and driven out, as opposed to the value outside coming through the backplane connector, being read and then driven into the local bus. So it works for the high side. The same thing for the low side. It's no different. I will run it very quickly to show you. Yep, everything is fine. So if let's take this, which is the driver that connects the local bus via the backplane to the rest of the system. The direction is now 0, so it's from B to A, it's an input. If something else tries to drive the low byte of the local bus, the direction should change and go from A to B. So let's say A low output enable is active, the direction changed, you see? If I go back to low, and then let's say B low is trying to drive the low byte of the local bus now, the direction changes. And the same thing as before, if I enable input bus low IO enable, and at the same time I say external data bus input enable, the direction will change, because now what it will be doing, it will be taking the value driven into the low byte of the local bus from the external data bus and driving it out via the backplane to the rest of the system. That's pretty much it. The only extra thing we can do is to put it now in standalone mode. So now in standalone mode, these two buffers connecting the local bus to the rest of the system will be disabled. So the card is now self-contained. It's not connected to the rest of the system anymore. And the dip switches are now enabled. You see dark green here. That means that the output enable is active. And on the other side, also dark green, the output enable is active. The direction is now frozen because it's always from the dip switch to the bus, not the other way around on both sides. So we are now in standalone mode. So let's now drive the internal bus with a volume. So let's say on the high side of the dip switch for the high byte, let's put ones on the high nibble. And for the low side, and you can immediately see on the LEDs, which are monitoring the high byte of the local bus, you can immediately see that you're driving this high nibble there. And for the low byte, we switch on the low nibble, so we know which value is in what part of the bus. And you immediately see on the LEDs, because these two buffers are always enabled, they are always driving the LEDs, whatever is on the buses. So now we have a high nibble on the high bus and a low nibble on the low bus. So we can start playing with it. You know, these two are disabled. We're not connected to the rest of the system. So what can we do now to fool around with it? Let me zoom out a little bit. Let's say we want to load A high with the contents of the high byte of the local bus, and we want to load B low with the contents of the low byte of the data bus. So what we do is we go here and say A high load enable is 1, and B low load enable is 1. And you can see already that the colors of the lines have changed, but the register value is there's still nothing there. It's all zeros, because we have to hit the clock. The registers will latch the contents of the respective bus only at the rising edge of the clock. So we have to come here to clock and up and down. So now we latched the contents of the bus into those two registers. Let me zoom out just a bit more. There we go. So now this LED bar is telling us there is a high nibble on the high bus and there is a low nibble on the low bus here. and they should have been loaded by A high and B low. Let's see, the LEDs showing the contents of A high now are identical here to this, so it was loaded correctly, and the LEDs for B low are identical to the bus, so the contents of the bus have been correctly loaded by B low. So now let's change the contents of the bus by playing around with the dip switches. So let's put an alternating pattern now, starting high and then alternating. So 1 0 1 0 1 0 1 0, and on the other side we do the other way around. Let's do 0 1 0 1 0 1 0 1. So we know what's coming from where. The contents of the registers will still be the same because nothing has been loaded. Only the contents of the bus have been changed. So now we hit, let's enable now B high to take this. So B high load enable and A low load enable. The two registers that we didn't load anything into right now. And then we go to the clock, one clock transition. So now what do we have? The contents of the high bus are now in B high, and the contents of the low bus are now in A low. And you see we have 4 different values, one for each of the 4 different registers loaded from the bus. So the loading is working. What we are going to do now, let's try to load A high with the contents of B high. And let's load B low with the contents of A low. So B low should have the same value as A low, and A high should have the same value as B high. Let's try to do that. So how do we do that? Well, first thing we need to do is to drive the internal bus from B high, and A low, because that's the source of the value we want. So let's drive the bus from B high output enable. So now the contents of the bus are the same as B high. And let's drive the low bus with A low. So A low load enable. And now the low byte of the internal bus has the same contents as A low. So now that the bus is being driven, we go to A high load enable and B low load enable. Now the values didn't change yet because we have to clock. So let's give it a clock pulse, high and low, and now A high and B low have the same value, and A low and B low have the same value. So driving the buses is working as well. We can now see if we are driving or receiving a value from the external data bus correctly. I didn't put any dip switch or LEDs, but it doesn't matter because we can look at the color of the lines to see whether they are 1, light green, 0, dark green, blue means floating, undefined, and red means a bus conflict or a line conflict. So it's blue now because we're not driving any value out to the external bus, and there is no value being driven to the external bus from elsewhere, so it's all floating, it's undefined. But if we set the control bits of these two buffers in the right way, then the buses, the internal bus or the local bus, should become undefined as well, because it's being driven from an undefined value, and we should see blue there. Let's see if that's what happens. First, we disable everything else. So, yeah, that's correct. Now we will enable I/O. Let's do it on the high part first. Internal bus high I/O enable goes to 1. Nothing changed yet because we need to do the internal bus high input enable, and then blue should be driven there. There we go. The LEDs turn off because there's an indeterminate value, and you see blue on the high part of the bus. And if we enable the low part for I/O as well, everything will become blue on the low part. There we go. So now let's go back and drive the bus now, the high bus from A high. So A high output enable, and the low bus from A low, so A low output enable. So now you see the value of the high bus is the same as A high, and the value of the low bus is the same as A low. And let's now drive this out to the external data bus. We don't enable external data bus input because it's not an input, it's an output. We just do the IO enable for the bus high. Now the external data bus should have the same value of A high, which A high is 1 0 1 0 and so on, and 1 0 1 0 and so on. And of course the other buffer will have the same value because they are connected together, but this buffer is tri-stated, so you see the same values there just because they are connected together. So here we see we are driving the value of A high, this register here, as displayed on these LEDs. We are driving that value via the local bus into the external data bus, which is what you would do if you want to store a byte in memory, for instance, or send something to an IO port. And we can do the same thing now, but for the A low value. So we enable the IO for the low part of the bus, so internal bus low IO enable. And now the value here should be the same as this, not the same as that. This one is 0 1. So let's see, 0 1 0 1 0 1 0 1, exactly, and it's precisely the opposite of this one. So now we are driving the contents of A low via the local bus, via this buffer, towards the external data bus. So this is outputting to the data bus, inputting from the data bus we just saw with the blue lines. And this is it. That's a test of the entire functionality. The little logic here is working fine. 2 OR chips, one AND chip. I'm not going to go into the details of the logic within because this is so simple. You can just get this simulation model from the GitHub directory, link in the description. Then you can click here and open them, so you see what's inside, and you can follow it. I mean, doesn't get much simpler than this. You can just follow what is being ORed, what is being ended, so you understand what's happening. So this is it. This is looking good. The functionality is what I wanted it to have. It's working both in in-system mode and standalone mode. It's driving all the lines correctly. There are no bus conflicts. This internal logic here prevents some of the bus conflicts. Other bus conflicts are prevented just in the way I encoded the instructions. So I'm happy with it. So let's now transfer this to schematics that we can use to design a PCB. All right, here are the schematics. There are 5 pages. This is the control page. Then there's a little bit about the buses, the registers, and then the register to ALU communication and IO. Very simple stuff. The control page is the most complex, so let's go over it more or less slowly. This is the circuitry for generating a local clock pulse by pressing a button on the board. In other words, standalone mode, not in system. So there is this push button here, which if you don't press it, it's closed. So when it's closed, this potential here, ground, will be on the top, and therefore this capacitor will discharge the ground, and this value will be a logic 0, which goes into a Schmitt trigger inverter. Here the Schmitt trigger is important because this whole thing here is a debouncing circuit. And in a debouncing circuit you want the Schmitt trigger. So it goes, is inverted once, is inverted twice. In other words, it's not inverted, it's just cleaned by the Schmitt trigger, and goes into this buffer as the local clock. There is another buffer here on top, which has the system clock coming from the backplane in case we want to use the board in system, and you select one or the other by either activating this bus or this bus. Actually, you either activate these 2 buffers. I said bus, I meant buffer. You either activate these 2 buffers when you are in system, or you activate these 2 buffers when you are in standalone mode, and they produce the same control signals. So the clock is produced here by this little debouncing circuit. You define whether the system is whether the board is in system or standalone with this little pin header. If the shunt is not placed, then this is VCC or logic 1, and then it's inverted once and twice, and then you get backplane output enable being 1, which is inactive. In other words, if you don't put the shunt, you are not in system, you are standalone. And the switch output enable is just the inverted, the negated backplane output enable, and this one will be 0 when we are in standalone mode, or active when we are in standalone mode. That's all there is to it. So these two buffers here, they are enabled by backplane output enable. So if this is 0 here and here, then these two buffers here are enabled by BPOE, and then the RF card will take its control inputs from the backplane. Otherwise, it's these two buffers here that will be enabled, because dip switch output enable will be low or active, and then the control signals will come from these two dip switches which are on the board, so we can set the control signals any way we want. This is just the power LED with a current limiting resistor, and this here is just the power supply circuit, which is the same as for the ALU card, so I'm not going to comment further into this. It's exactly the same. Now we've seen here that this entire thing here is to select whether the control signals come from the backplane or from the dip switches. So what am I doing? Yeah. This entire thing here decides whether the control signals come from the dip switches or the backplane connector. Once that choice was made, you get the same control signals, and the clock, because the clock is the first one. You get the same control signals on the other side, but now I add an L to their name to say local. Local means after selection. So this local B high load enable can either come from the backplane or can come from a dip switch. Either way, it will the result will be in this line here. Now the first thing you do is you pass these local lines now through another buffer, 1 kilo ohm resistor network, and you send them to an LED bar so you can see what the control signals are. The same thing for the rest down here. I'm having to use two buffers because there are a lot of control signals this time, more than 8. So I think there are 12. Yeah, 12. So I need two buffers for each selection and two LED bars to show everything. Now the selected signal then goes through the inverters, because in the control word we have positive logic. Buffer enable is active high, because if it were active low, when we reset the computer and the pipeline registers go to 0, all buffers will be enabled and we'll have bus conflicts. So in the control word we have to have positive logic, but we know that the chips require negative logic. The signals are active low, so we have to invert everything. So for every signal, like local B high load enable, it passes through an inverter and comes out as the local negated B high load enable. So LN instead of just L. And it's the same convention for all the other signals. And that is pretty much this chart. Then the bus themselves, these three ICs are the control logic that we discussed in the simulation. And they feed the directions and the output enables of some of the buffers here. These are the signals of the internal bus high as they come through the backplane connector. They go through a resistor network of 33 ohms to absorb some ringing, and then they have their own buffer, which determines whether whether this card is in system or not, and what direction the buffer should work with, A to B or B to A, depending on whether it's an input or an output, like we discussed. And then it goes again through 33 ohm resistors to absorb the reflections and the impedance mismatches. And then we derive the signals of the local bus high So the local bus high is just the segment of the internal bus high in this particular card. That's basically it. And the same thing happens for the low byte. We have the signals from the internal bus low as they are connected in the backplane. 33 ohm resistor network to absorb ringing its own driver, and then 33 ohm resistor network to absorb the ringing in the local bus low. All right, now these buffers here are for the dip switches. These are the two dip switches, S3 and S4. These are 10k ohm resistor networks to tight low, so the switches actually work. And these again are the same lines: local bus high and local bus low. So these lines are the same as here. I'm not using lines to connect them, because then it's a mess. You have green lines everywhere, you don't know what is what. And the same lines appear 1/3 time, the local bus high here and the local bus low here. And in this case, they have, again, other dedicated, what am I doing? Sorry about that. They have dedicated buffers to drive LED bars. And they do that via 1k ohm resistors to limit the current. So this is just to drive the LEDs to see what's on the bus. This stuff here is to drive the settings of the dip switches into the bus, and this stuff here is what connects the local segment of the internal bus via the backplane connector to the rest of the internal bus as it appears on the other cards. And this is just the control logic we discussed in the simulation. Not too complex. I mean, it may look complex with all these signals and all these lines, but if you remember one episode ago, you will realize that this is actually all very simple. You just need to you spend some 10 minutes to get used to the naming conventions and the names of the signals. Then everything falls in place very easily. Now, these are the actual registers. These are the 4 registers. They receive the contents of the local bus. So in the case of register A high, it will receive let me see, local bus high 7, local bus high 6, local bus high 4, local bus high 5, 4, local bus high 3, 2, 1, and 0. These are the inputs. And the outputs will be register A high 7, register A high 6, register A high 5, register A high 4, and so on and so forth. The inputs for B high are the same because it's connected to the same high byte of the local bus, and the outputs are different because they have their own names: register B high 7, register B high 6, register B high 5, and so on and so forth. And this is the same thing for the low byte of the bus, namely register A low and register B low, which have the same inputs but different outputs. Then the outputs of the registers, so not the outputs of the buses, but the outputs of the registers themselves, go through dedicated buffers that drive LED bars through 1k ohm resistors for current limitation. So we can see what the contents of the registers are, regardless of the contents of the buses. And here, these two buffers here will determine whether A high or B high, the contents of A high or B high, if you look at the signals going in, these are the lines coming from register A high and register B high. These two buffers will determine whether one of them, or none, but whether one of them drives the local bus high via a 33 ohm resistor network to reduce reflections. I use this 33 ohm, these 33 ohm resistors every time I'm driving something into the bus, because bus lines have lots of fan out, and lines with fan out with branches, lots of not fan out, lines with branches tend to have lots of reflections. So every time I drive a bus line with all those branches, I use 33 ohm resistors to reduce reflections. And even when I'm reading from the bus, I try to do that as well, to reduce the reflections on the input side as well. 33 ohms, you can see these resistors, you can interpret these resistors as a low-pass filter, because these resistances coupled with the intrinsic parasitic capacitances of the lines will give us an RC filter that is essentially a low-pass filter. And reflections tend to be the higher harmonics because, PCB lines are relatively short in relation to the speed of light. So what tends to get reflected are the very high frequencies with very small wavelength, even at the speed of light. So we have to use a low-pass filter so to eliminate the high stuff. And this is the same thing, but for the low byte of the bus, which can be driven by a low or below, or none of them, and depending on these control lines here. So that's the register page. Now the register to ALU, this one is straightforward. The lines coming out of each register, not the bus, the registers, like register A high, register B high, register A low, and register B low. They go through again their own buffers through a 33 ohm resistor network, and they go to the ALU via the backplane. Now, why am I using 33 ohm resistor networks for these lines? These are not bus lines. They're point-to-point connections. They go from here to the ALU card, one by one. They don't have branches. They don't branch out at all, fan out of one. Why am I using 33 ohm resistors? It's because of the impedance mismatch of the backplane connector. I should have done that also for the register flag signals, the 6 signals from the register flag that go from the ALU to the control card, which we didn't do yet. They also go through the backplane connector. And I didn't put 33 ohms there because they are not buses. Again, they are point-to-point connections. But I regret that, and the reason is the impedance mismatch of the backplane connector, which produces its own reflections. So I put the 33 ohm resistors here to absorb the reflections from the backplane connector on the driver side. And in the case of the flags, the 6 flag signals from the ALU, they don't have these 33 ohm resistors on the driver side, on the ALU board. I forgot it, or I decided not to do it and then I regretted it. But I will put them on the receiver side. I will put them in the control card, because ultimately, if the control card doesn't see the reflections, then it doesn't matter, right? So the little low-pass RC filter will be on the receiver side. Normally, when you see people using these 33 ohm resistors, you will see them telling you, you have to put them as close as possible to the driver pin. And when they say that, they are thinking of these 33 ohm resistors as impedance matching to the PCB traces, because the output impedance of a typical TTL chip is around 15 to 20 ohms, and the PCB traces are 50 ohms typically. So to match the impedance of the two, you add 33 ohms right next to the driver pins. So the output impedance becomes 50 ohms, which is the same as the trace, and then you don't have the reflections. You don't even create the reflections to begin with. That's a valid way of thinking about that. The other way of thinking about that is what I just mentioned earlier. You can think of these resistors as forming a low-pass RC filter together with the parasitic capacitance of the lines. And if you think of them this way, then it doesn't matter where you put them on the line. Wherever they are, they will absorb the higher harmonics and absorb the reflections anyway. So the difference is whether you're thinking in terms of avoiding the reflection or whether you're thinking in terms of absorbing the reflections that will happen. It doesn't matter. In my experience, it doesn't matter much. Even if you don't put these resistors close to the output, to the driver pins, they will still work because they work as low-pass RC filters. And in this case here, And in the case of the flag signals of the ALU board, my concern is not impedance matching with the PCB traces. My concern is the reflections from the backplane connector. And if that's the concern, then it doesn't matter where you put them. Whatever in the entire network, in the entire net, the filter will be, it will absorb the reflections, whether it's on the driver end, the receiver end, before or after the backplane connector. There will be, if I put the filter on the receiver's end, there will be reflections on the driver end, but it doesn't matter because the receiver will not see it anyway. One valid criticism would be to say, well, if you are actually doing an RC low-pass filter, then why 33 ohms? Because 33 ohms, that value, the rationale behind that value is to match the impedance of the trace. But if that's not what I'm doing, if what I'm doing is absorb reflections from the backplane connector, then maybe there should be another value that is better. Maybe, but 33 ohms works. 33 ohms work just fine. So I didn't characterize the backplane connector to calculate its impedance. Sorry guys, this is a hobby. I am retired from technology. I'm not going to do anything that I don't find fun and I don't find cool. And to be honest with you, the only way to really know for sure whether it's better to put the resistors right at the driver pin or somewhere else, the only way to know that is to run a simulation, starting from Maxwell's equations for your specific circuit, which takes a lot of time, a lot of computing power, takes expensive tools that require licenses, and I ain't gonna do that. I ain't gonna do that. I'm doing all this stuff not even to make this computer as fast as possible. It's not about speed. This is an educational platform. It's about understanding how it works. I'm doing this to increase the robustness, the reliability of it, not to make it faster. That's all. That's the only reason. So it's not justifiable to me to go through, Maxwell equation simulations to decide where exactly I should place this stuff. Sorry. And this is the I/O diagram where we have the actual backplane connectors and the signals that go into them. And these are the buffers for the external data bus. So these are the lines of the external data bus 0, external data bus 1, external data bus 2, and so on and so forth. And these are the buffers that connect them to the local bus high and the local bus low. And again, local bus high is the segment of the internal bus high in this particular card, and the local bus low is the segment of the internal bus low in this particular card. And this is just 10 decoupling capacitors for a board that is 24.4 times 24.4 centimeters, about 10 100 microfarad decoupling capacitors should do. This is really rule of thumb. To really know what you need to follow the power distribution network and calculate the bottlenecks. I ain't gonna do that either. Nor are you interested in this. Let's be honest. You're not designing a board for an Apple computer. And these are the bypass capacitors. It's 1 per IC, and these are 100 nanofarad ceramic capacitors just for a local bypass. And this is it. Next thing is the board itself. And here it is. Come on. There we go. That's the board. I will reduce myself a little bit, so we have the space to see the board. First, an overview. These are the 4 registers, A high, B high, A low, and B low. These are the register chips, the 74HC377s. Very simple. This circuitry here is just the drivers and the LED bars to show the contents of each register. So this is the LED bar. These are the 1K ohm resistors for current limiting, and this is the buffer dedicated to drive the LED bar for AH. And the same for BH, AL, and BL. So on these LED bars here, we can see the contents of each register. Then there are more buffers, 4 dedicated buffers with 33 ohm resistor networks connected to the outputs, driving the lines that go to the ALU card. So the contents of all 4 registers bypass the internal bus and go straight to the ALU card here via these lines here, 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 and here to the backplane. So I put the 33 ohm resistors there to absorb reflections from the backplane so they don't go across the backplane towards the ALU card. Now, this here on this corner, the upper corner here, what we have, let me see. These are the LEDs, respective 1K ohm resistor networks and respective buffers that show the contents of the local bus, which is the segment of the internal bus in this card. And this is the local bus. You see these lines along the left side and the top of the board. This is the local bus. So the registers can latch the value of the local buses because the local bus wraps around until the top of the register chips. So you can load a value into the register from the local bus lines here on top. And from the same lines, you can drive LEDs to show what is on the local bus, not what is on the registers. These LED bars here show what's on the registers. These bars show what's on the bus itself. Then we have the 2 dip switches with which we can drive the high byte and the low byte of the internal bus. They have their own drivers and the resistor network here to pull the values down so the switch works. And the buses can be driven from these 2 switches here, S3 and S4, which drive the local bus or the internal bus lines here along the left side of this card. These 3 chips are the control logic we talked about. Now, this complex here, there are 4 buffers and 2 resistor networks of 33 ohms. What they do is these 2 buffers will select whether and which of registers A high or B high is driving the high byte of the bus. So these just drive the high value of the local bus into the local bus, and that value will come either from A high or B high or none if you're not driving the local bus through these buffers. And this is the same for the low part. These 2 buffers will drive either A low or B low or neither to the low byte of the local bus via the resistor network of 33 ohm resistors. Now, these 2 buffers connect the local bus to the internal bus of the other cards via the backplane, via these lines here of the backplane. And the buffers have resistor networks of 33 ohms on both sides. On this side to absorb the local reflections of these bus lines, because again, these bus lines, they have a lot of branches. I can actually show it. So if we take one of the lines, let's take this line here. Look at how many branches it has. You see, I can count 1, 2, 3, 4, 5 branches on each of the lines. And this branching out is what causes reflection, because each segment of the branch has its own resonating frequency, and then because the rise and fall times of these signals tends to be very short, you have higher harmonic contents which will resonate differently in each of the branches and therefore reflect and produce ringing with different frequencies. We absorb all that, well, not all that, but a lot of that with these 33 ohm resistors. And on the other side, it's to absorb the reflections from the backplane connector, which is a major impedance mismatch. Now, this buffer here and this will drive either the contents of the low byte of the local bus or the high byte of the local bus into the external data bus, which is connected to the backplane connector here. And they also go through the 33 ohm resistor network to absorb the reflections from the impedance mismatch of the backplane connector. We're almost there. And now the control signals come from the backplane connector in this area here, or they can be set by these 2 switches with their respective little resistor networks to pull the signals down so the switches work. And these 4 buffers here will then select whether they come, the control signal values come from the backplane or from the switches. Either way, the result is inverted by these 2 inverter chips, and then they are spread around the board to control everything. And now, and that's the end, these are the 2 LED bars that show the values of the control signals. So that's DS2 and DS1. And they are driven by their own buffers via 1K ohm resistor networks for current limiting. And this on the side here is just the logic that we use when the board is used in standalone mode. There is a little button there for the clock. There is a little debouncing circuit and a header for us to decide whether the board is in standalone or in system mode. And here on the side, it's just the simple power supply, which is exactly the same as we discussed before. Now, the decoupling capacitors, the 10 electrolytic decoupling capacitors, are distributed across the board. The power distribution network, I've implemented that through copper fill. So the red areas are the copper fill that transmit the VCC signal. And where do I put this decoupling capacitor has not only to do with distributing them evenly across the board, but understanding how the copper fill will actually form the PDN, the power distribution network, to identify bottlenecks. And if you have a bottleneck, you may want to relieve the bottleneck by having a thicker line connecting VCC, or you put a local decoupling capacitor, so you have a little battery locally in case there is higher demand on the power lines. But to analyze the power distribution network, if you build it with copper fill, can be tricky and requires time and patience. Let me show you just a tiny part of an analysis so you understand what is entailed. These are two 245 chips. They drive 16 lines. And they're not, so they require quite some power to drive those lines. And their power pins are here and here, and they are connected to this red copper area. And you think, oh, plenty of connections, right? We don't have a problem with power here. Well, think about it. Follow the red. Goes here. Oh, that's a dead end. Oh, along this line it's a dead end. Oh, here it goes up. Oh, it's a dead end. Dead end here. Oh, along this line it's a dead end. Oh, it's a dead end here on the side as well. So all of this here is a dead end. So let's go down. Let's go to this side instead. Okay, it comes here. Oh, here's a dead end. Let's zoom in. Here's a dead end because there's a signal line here preventing the copper fill from going further. So you have to go up, go up, go up, go up. Oh, it's not a dead end, but look how thin this is. If all the power for this entire part of the circuit is coming through this thin little line, we have a problem, Houston. And that's what you have to know, because if you do a copper fill and then you ask the tool, are all my nets routed? So I click in there, are all my nets routed? Oh, it tells me yes, 397 nets are routed out of 397. Everything is routed. What it will not tell you is that power is going through a tiny bottleneck. So it is routed. The tool will tell you, yep, it's fine, everything's okay. And then the thing will not work. In this case, it's not really a problem, because if we follow this further, we will see that the power can also come from here, here, here. You see, it goes into this area here. It's a dead end on this side, but going up, look, there's a lot of space here. There is more space here, 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 here. Through this side, this way, that way, that way. It goes up, ooh, and then there's a lot of power. So it's okay, but it was not when I did the copper fill at first. If you look at the bottom layer and we hide the copper area, what you will see in horizontal blue lines here, you see thick horizontal blue lines. These lines are for bringing power everywhere in the circuit, in addition to some bottlenecks of the copper fill, because the copper fill on the top is VCC, on the bottom it's ground, So in blue, the copper fill is ground, but I'm adding dedicated lines to sort of stitch the copper areas on the top layer via the back layer and avoid these bottlenecks in different islands of copper fill. And that's what you see in these blue, thick blue lines, and there are even vertical ones. It's to make sure that power goes from this pin everywhere, even when the copper fill has limitations. And if we show now the copper area, you see most of the blue here is ground, except these thick blue lines here with lots of vias, which are meant to stitch the copper islands on the top layer via the back. That's the idea. You also notice that most of the time I don't let the copper fill go in between lines that are close together, because I don't have a ground plane to stitch the copper fill in between these lines. And if I don't stitch them, they actually can contribute to more cross-coupling as opposed to reducing cross-coupling, because at the wavelength of the higher harmonics in the circuit, at the speed of light, it would just take too long to actually reach ground potential. And what will happen is that two neighboring signal lines, like this and this, if there were a floating copper fill here at the ground level in between, without the actual ground plane, the copper fill would float, and these two lines would couple to one another via the metal, because the metal is effectively floating at the speed of light, at the wavelengths of the higher harmonics in the circuit. So I prevented the copper fill from getting in there, both by playing with the margins and sometimes by using strategically positioned vias of a different net to prevent the copper fill from getting in there. Let me show you some example of that. On the top, it's easier. So if you look at the top layer, these vias here, they are ground vias, so they don't belong in the same net as the copper fill, because the copper fill is VCC, and they are used both as return path vias for the respective signal vias next to them, but they also prevent the copper fill from flooding in between two lines. That's why they are placed where they are placed. And sometimes I add a via that's not even a return path via. I add it just to prevent the copper fill. For instance, this via here, that's a ground via. See, ground. The copper fill is VCC. Now, this is not a return path via for anything. It's just sitting on top of the copper area in the bottom layer, which is ground, and it's preventing the copper fill of VCC to get in between these two lines, which I didn't want to. That's why you see some of it. And as for the rest, it's just some usual routing, placement and routing tips. For the bus, I could not avoid all the branching. As you see in this bus line highlighted in white, there are lots of branches. And it's unavoidable when you're designing a CPU. There are internal buses, you can't avoid it. You have to live with the reflections and take countermeasures like the 33 ohm resistors that I always use. But when I can avoid it, I do. For instance, these lines here, they do not have branches. If you look closely, you see that they have high fan out. They go to several places, you see? But they do not branch. They are a snake. They go from one place to the other, and from the other to another, and from that to another. They don't branch out. It's just a straight, not a straight line. It's just like a snake without branches. And I did this on purpose because I could have connected these buffers here to the bus via horizontal lines. Let me show explicitly. I could have stretched these horizontal lines here further and connected the buffer to them here, instead of connecting these buffers there going upwards, which is what I did. These buffers connect upwards. You see, they go up. Now, why did I choose this as opposed to the alternative I just discussed? Well, to make sure that as many nets as possible are snakes, as opposed to, I don't know, crabs, lines that branch out several times, because you just get a lot more reflections if you do it that way. Yeah, that's pretty much it. You try to keep the lines as short as possible, but not shorter. You try to keep them as far apart as possible. There is no need to crowd them close together if you have the space. You just increase the chance of crosstalk if you do that. Yeah, that's it, ladies and gentlemen. I can hide the copper fills so we can see the routing. What I was talking about is I could have used these lines and stretched them out and connect to these buffers, as opposed to connecting the buffers vertically to the registers. And I did that to avoid more branching than I needed. And you try to follow the rule of thumb of preferential directions for each layer, but you don't follow that blindly. So let me give you an example of that. The top layer in red, the preferential direction is clearly vertical. You see vertical here, vertical here, vertical here, diagonal almost vertical here all over the place, vertical here all over the place, there and there. But because I bow the local bus here with a 90-degree turn, I didn't switch these lines of the local bus to blue. Because one, I didn't need it. I could just maintain them red and avoid one more via, one more layer change. In other words, one more impedance mismatch, one more chance for reflections. So I ignored the rule of thumb here, but then I inverted everything. You see, normally blue is horizontal, so that's the blue layer. Almost everything horizontal, but because I changed the convention on top, I was consequent with that. Now blue is vertical on top, you see? Close to the top, blue is sort of vertical. And don't be afraid of diagonal lines, because some people, they look at these old retro boards from the 70s and 80s, and you will not find anything diagonal there. Why was that? Well, it's because they didn't have CAD tools like we have today. And it's much easier and faster to get a first routing that works, that connects everything, if you stick to only horizontal in one layer and only vertical in the other layer. You have a much higher chance of succeeding first time. And that's why they did that. But now with CAD tools like this, you don't need to follow that rule blindly, because otherwise you just have a lot more vias than you need, a lot more impedance mismatches than you need. You use the rule only as a rule of thumb, as a best practice. But when you realize that it's definitely better to ignore or even invert the rule, you do it. You just have to know what you're doing. And I chose to do that. I chose to, when I bended the local bus here, I inverted the rule. Consequently, on the top part of the board, red is horizontal and blue is vertical, even though in the rest of the board, it's the other way around. And I did it because I knew I could. I have a CAD tool that shows me all the rat lines, what needs to be connected with what, and you can play around with it, and you know that you can do it, and it will save you more impedance mismatches. So that's what I did. Let me show you the copper area again. This is becoming a very long episode. The reason I'm doing this long episode is that I want to publish as soon as possible, because I'm ready to send this to the manufacturers, and I'm going to give you guys 24 hours to tell me what errors I made and give me good suggestions before I send to the manufacturers. That's why I'm compressing everything in this one episode, is because I want to send it as quickly as possible. I want to publish everything quickly. We can have a look at a model of the board, a 2D model, to see what it will look like. And it will look like this. That's pretty reasonable to me. We can even look at a 3D model, which is incomplete because I never bothered to load all the little 3D models of every component. I'm just too lazy for that. If I were designing something that needed to fit in a particular case, then I would bother with all the 3D models. But like this, no. So I don't have the 3D models for the resistor networks, for the LED bars, the dip switches. But if you can, in your imagination, fill these empty slots here, these empty areas with the respective chip-looking things, you can have an idea of what the board will look like. And yeah, it looks good to me. I used the space as much as possible, kept the lines apart as much as possible, using the entire space I made available to myself. So this is looking good. All right, so this is it. The simulations tell me it will work. That's not guaranteed because in moving from the simulation files to the schematic entry, you have to add things, you have to change the names of some lines, and you may connect some lines wrongly. So probably there will be errors, but we only find them if we actually manufacture stuff and have real hardware in our hands. So I'm going to send it 24 hours from now. Tomorrow at the same time that you're watching this right now, it will be sent. So you guys have 24 hours to help me out and make suggestions or corrections. If I missed something that you spotted, whatever, you can let me know. All right, thanks for watching, and I will see you next time, hopefully with real hardware for the register file card. Till then, take care.